Hello all and welcome back to On the Spot STEM. And today we will be tackling the 2019 Aime I problem number 12. And the problem reads, given f of z equals z squared minus 19z. There are complex numbers z with the property that z, f of z, and f of z are the vertices of a right triangle in the complex plane with a right angle at f of z. There are positive integers m and n such that one such value of z is m plus root n plus 11i. Find m plus n. So in essence, we are dealing with a complex number problem involving rotations. And so let's draw a quick diagram. So we have f of z at the right angle vertex, and we have f of z at one potential vertex and z at another vertex. Note that this could be flipped, but it's actually irrelevant for the problem. And we know how to deal with rotations dealing with complex numbers when we're at the origin, when the origin is the point about which we're rotating. But in this case, f of z is the point about which we're rotating. So what we can do is actually shift this entire problem back to the origin. We can subtract f of z from all of these complex numbers, which yields the following diagram. 0 is here, and we have z minus f of z in place of z, and f of z minus f of z in place of f of z. So what we note that is if we rotate f of z minus f of z by 90 degrees to z minus f of z, to that particular angle, then one will be a scalar multiple of the other. So what we can write is that we can use our rotation formula for complex numbers, that f of z minus f of z times cis of 90, where cis is cosine plus I sine. Cis of 90 is simply I. We can write I equals z minus f of z times some constant k. So now what we can do is rearrange a little bit. We can divide z minus f of z on both sides. We can divide by I on both sides. And what we get is the following. F of z minus f of z over z minus f of z equals k over I, but k over I is just negative ki. So essentially what this is saying is that f of z minus f of z over z minus f of z, the thing we have on the left hand side, has to be pure imaginary, or in the sense that it is a scalar multiple of I without a real part. So what we can do now is use the fact that f of z equals z squared minus 19z to simplify the problem. So we note that, let's do the denominator first. It's most likely easier. And since we are dealing with, just simply being a scalar multiple of I, we don't really care much about the sign of the denominator. So we can change the denominator simply for simplicity to f of z minus z. So now we can simplify. The denominator simply becomes z squared minus 20z, because we're taking z squared minus 19z and subtracting z. And the top becomes the following. So the top can be written as, we note that z squared minus 19z is z times z minus 19. So f of z can be written as z squared minus 19z times z squared minus 19z minus 19. Let me erase this over here. Minus z squared minus 19z. So we can do some cool factorization on the top, which severely helps us. So the top we can factor out as z squared minus 19z. And this becomes z squared minus 19z minus 20 over, let's factor this as z times z minus 20 on the denominator. And continuing our factorization, we get that. So in essence, we can factor the top as z times z minus 19 times z minus 20 times z plus 1 over z times z minus 20 on the denominator. And many things cancel out here. The z's cancel out, the z minus 20s cancel out. So what we're left with is z minus 19 times z plus 1 is pure imaginary. And the nice thing about the problem is that it actually gave us the imaginary part of z, 11i. So what we can do is let's let at this point z equal a plus 11i. So what we can do is we can stick in this expression for z and simply set the real part equal to 0, since we know that this expression has to be pure imaginary. So we can do this. And so it becomes a minus 19 plus 11i times a plus 1 plus 11i is pure imaginary. So we simply only care about the real part, and the real part is a minus 19 times a plus 1. And we simply took a look at the I terms. 11i times 11i is negative 121, and this has to equal 0. And we can solve this quadratic very easily. So this quadratic is simply a squared minus 18a equals 140. And solving this quadratic through the quadratic formula, or however way we want to do it, we get that a is 9 plus or minus the square root of 221. And looking back at the problem asks, well, there's one such value such that z is m plus square root n plus 11i. So clearly our value is 9 plus square root of 221 plus 11i. And m plus n is 9 plus 221, which is 230. And we are done.